Welcome to a discussion of the F-test for the joint significance of a subset of independent variables. In this discussion, we're going to talk about how to perform the hypothesis test for the joint significance of a subset of slope coefficients to see if they're jointly statistically significant. Here's an example. Here's the original regression. The original regression model has three independent variables, x1, x2, and x3. And for example, after testing for individual significance of x2 and x3, they're individually statistically insignificant at the 5% level. In this case, we may want to know if, even though they're individually statistically insignificant, if together or jointly x2 and x3 are jointly statistically significant. Here's an example. It's the same housing price example. So the original model was housing price is a function of lot size, square feet, and bedrooms. If we run this regression and regress housing price on lot size, square feet, and bedrooms, here's the results. We can see that there's only 10 observations because n minus 1 is 9, so n 9 plus 1 is 10. And in this case, if you look at the p-values, first of all, the overall significance, if they're jointly significant, beta 1 equal beta 2 equal beta 3, that null hypothesis equals 0. That gets rejected because this is the p-value for that F-test. And then here we can see that lot size is individually statistically significant because the p-value is quite small, but square feet is statistically insignificant because this p-value is obviously greater than 0.05, it's 0.26 essentially. And then also the p-value for bedrooms is statistically insignificant because this p-value is very large. So let's review. Lot size is individually statistically significant. Square footage in bedrooms are statistically insignificant. So even though they're individually statistically insignificant, they could be jointly statistically significant. So that's what we want to test. Here's the hypothesis. In this case, we want to see if beta 2 equals beta 3 equals 0. There's no linear relationship jointly between x2 and x3. And then the alternative hypothesis, HA or H1, is that at least one of beta 2 or beta 3 jointly or individually explains why. And so it tests both joint and individually. In this case, we know that they're individually statistically significant. We want to see if they're jointly statistically significant. In this case, we have kind of new terminology that we want to use. We have the unrestricted model, which is our original model. So this was the model that we estimated over here, right? This is the model. This is the thing that we estimated. We call that our unrestricted model because there's no restrictions on it. And then what happens is we impose the null hypothesis on the unrestricted model, and that gives us the restricted model. Imposing this null hypothesis means that beta 2 equals 0 and beta 3 equals 0, which means that this term drops out and this term drops out. So in that case, we're left with the restricted model, or again, the model that we get after imposing the null hypothesis. That's our restricted model. And in this case, we have y equals beta naught plus beta 1 x1 plus, and then I put a little asterisk by this error term because it's different, obviously, than that error term because x2 and x3 now live in there, whereas in this model, they did not. So I was just trying to say that this error term is different than that error term. This is our unrestricted model. This is our restricted model. We need to run two new regressions. The first regression is with our restricted model. The second one is with our unrestricted model or vice versa. Okay, here's our test statistic for this hypothesis. So it's the unexplained sum of squared from the restricted model, subtract off the unexplained sum of squared from the unrestricted model, and divide by Q. Q is the number of restrictions or the number of equal signs in my null hypothesis. So you just count the number of equal signs in your null hypothesis. That's what Q, or the number of restrictions, is. So we can see in this case that there's two equal signs, 1, 2. So in this case, Q equals 2. And then so that's our numerator of our F statistic. And the denominator of our F statistic is our unexplained sum of squares. It's always the unrestricted model in the denominator. And then this n minus k minus 1 is from the unrestricted model. So these have to match. Obviously, there's a different, same n typically, but different k between the restricted and unrestricted. So it's important to note that the denominator has the unrestricted k. Okay, the other form of this test, instead of the unexplained sum of squares form, is the r squared form of the test. It's a little bit less general, but most of the time in this class we can use it. And it's easier because most people report the r squared associated with their regression, so you just take out the r squared. So basically you flip-flop these two things. So this is the r squared unrestricted minus the r squared restricted over q, which is the same number of restrictions, and then 1 minus the r squared unrestricted divided by n minus k minus 1, again from the unrestricted model. Okay, so let's see this in action or apply this formula to the data that we have. Well, first of all, let's discuss the critical value, so the rejection rule. So we're going to reject H naught if our F stat is greater than F of alpha, which is typically 0.05, Q, which is our numerator degrees of freedom right there. It's in the numerator, so that's why this is the numerator degrees of freedom. And then these are our denominator degrees of freedom, n minus k minus 1. So as I've already said, that for this test, you need to run two separate regressions. The unrestricted regression, which you would have already run because that's how you figure out what you want to run for your restricted regression. And then secondly, your restricted regression. Here's our unrestricted regression, and this is our unexplained sum of squared unrestricted. This is the number we want to pull out. Again, it's next to the residual row. And this is actually, the 6 will be our n minus k minus 1 for our denominator degrees of freedom. Remember, this comes from our unrestricted model. So this is our unexplained sum of squares. And then this is our restricted model. Our restricted model, we still have housing price as our y variable or a dependent variable. And then lot size is the only thing that remains because, again, we impose the null hypothesis to get this restricted model. So this is our unexplained sum of squared for our restricted model, this number right here. And then we can see that Q equals 2 because 1, 2 equal signs in our null hypothesis. Once you get those two numbers, the unexplained sum of squares unrestricted, unexplained sum of squares restricted, and then Q, which is 2, n minus k minus 1, again, that comes from the unrestricted model. It's the number that's in the same row as the residual. Okay, then you just put it into the formula. It's not that big a deal. Here's this number, so 621, 726, 567, that's that number. And then 456, 205, 475, that's that number right there. And this F statistic always has to be positive. So for the for the unexplained sum of squared version of this test, it's always the restricted minus the unrestricted to make sure this is a positive number. The F distribution is always positive because it's a ratio of variances. And then in the denominator, this comes right here from our unrestricted model. And then again, these are the degrees of freedom associated with our unrestricted model. After you do that, you just do the math, and this is our test statistic. So we're going to reject H naught if our F stat, this test statistic, this number right here, is greater than this critical value or this number here. So we need to figure out how to get that number. Here we go. This is the F table. I just copied this F table from, I took a screenshot from the tables that I have posted under the assignments tab in Blackboard. And this is how you read the F table. And this F table is for alpha equals 0.05. So for a 5% significance level, which is the only thing we're going to do in this class. If we wanted to do it for a 1% significance level or a 10% significance level, then we would have to get a new F table. But in this class, we're only going to have alpha equals 0.05. We can see along the top, there's numerator degrees of freedom. And then along the sides, there's denominator degrees of freedom. The numerator degrees of freedom are 2 because that lives in the numerator. And then the denominator degrees of freedom are 6 because that's the thing that lives in the denominator. Therefore, you just, where your hands match, I just put little bitty arrows here, or fingers match. So 2 for numerator, 6 for denominator degrees of freedom. Wherever those two things are, that's your critical value. We can see here that I've already picked that out. So we're going to reject H naught if our F stat is greater than 5.143. And then our decision is because 1.0885 is not greater than this number, we fail to reject the null and conclude that square feet and bedrooms aren't jointly significant. So they're not only individually insignificant, they are individually insignificant, they're also jointly insignificant. Okay, and then instead of doing the sum of squared unexplained version of the test, we can instead do the R squared version of the test. We have already run these regressions. You just pick out the R squared from these regressions. R squared unrestricted, R squared restricted. In this case, again, it's flip-flopped because this needs to be positive, and then the R squared unrestricted because it explains more of the variation of housing price. It should be larger. The R squared restricted should be smaller, so that's why it's flip-flop from the sum of squared unexplained version of the test. So 0.9860 minus 0.9809 divided by 2, which is Q, and then 1 minus, again, this comes from the unrestricted model, this 6 comes from the unrestricted model, and we get the same number. Every once in a while, you'll get a number a little bit different just due to rounding error. And don't flip. So it should be about the same, but every once in a while, a couple of these digits, again, especially if you round to 4 decimal places like I typically do, they may be a little bit different, but in general, it's very, very close. You can use either version of the test most of the time. We'll talk about next chapter when I do a discussion of the Chow test, when you need to worry about not using the R squared version of the test. You can always use the sum of squared unexplained version, not always the R squared version, but in this type of test that we're doing right here, as long as your Y variable is the same between the two regressions, you're fine using either version. And then our decision is the same because we have the same test statistic, and then notice that you have the same test statistic regardless of if you use the sum of squared unexplained version of the test or the R squared version of the test. Okay, so why I brought in these slides about multicollinearity is that the reason that we could potentially have individual insignificance but joint significance is due to multicollinearity. So I just wanted to remind you guys what multicollinearity was and talk a little bit about why it might be a factor. Multicollinearity is when two of the independent variables are highly linearly related, so they are explaining a lot of the same thing. It's not perfect multicollinearity. Perfect multicollinearity is if these two independent variables have a correlation coefficient of 1 in absolute value. Again, it could be 1 or -1. But multicollinearity means that the correlation coefficient is high but not perfect between the two independent variables. Here's a Venn diagram of what is happening. I know it's a little bit sloppy, sorry. It's a little embarrassing. But in this case, we can see that jointly, these two variables explain why, but individually, there's just not that much information that goes in. So said another way, once I remove the effect of x2 from x1, and then I try to explain why using that impact, it's not that big. It's just that little orange part. And then here, same idea, that when I use the variation, once I remove the variation in x1 from x2, there's not that much left of x2 to explain the variation in y. So in this case, these could be jointly insignificant, individually insignificant, but jointly significant, because together they help explain y, but individually they don't. What are the implications of multicollinearity? Unlike perfect multicollinearity, our x prime x matrix is still invertible, so we can still get OLS estimates. OLS estimates are still unbiased if we have multicollinearity. The problem is that standard errors can become large, again, because there's just not that much information going in to getting this beta 1 hat and this beta 2 hat. And then secondly, and why it pertains to this joint F test of the subsets of testing a subset of independent random variables is that variables can be jointly significant, but they're individually insignificant because, again, not that much information goes in there. Okay, thank you so much for listening to this presentation. I know that this material is difficult, so I think it's good that I put it in this kind of presentation so you can stop and watch, and you can do it yourself. You can go to Excel. We have the data set online. You can actually estimate these regressions and make sure you know where these numbers come from. This is one of the more important things that we can know how to do to figure out significance of a subset of random variables. And then I'm sorry for the noise in the background. My daughter was doing her bounce back for lacrosse, so if anybody was wondering what that annoying banging was, that was the lacrosse ball off the bounce back. It is what it is. Thank you guys for listening. Hope this helps.